Welcome back. Today we're going to continue to talk about something we began addressing in class earlier, and that is binomial probabilities. One of the main issues in dealing with a binomial probability situation is recognizing that we actually have a binomial probability situation. One of the keys to that is that we can break the problem down into having exactly two outcomes. One being a success, the other being a failure. So we must be able to view it as a success or failure, or good or bad, and things like that. We have to be able to break it down into those two things occurring. Also, another key is that we have a fixed number of trials, meaning we know how many times we're going to try something, and we are trying to identify a number of successes out of that number of trials that we're going to have. We'll look at some more examples here, but that fixed number of trials we always call n. That's what it represents, is the number of times that we're going to actually try to be successful with what we're doing. When we have those two things in place, the fixed number of trials and a success or failure situation, we use the formula given here. Probability of x is equal to n factorial over n minus x factorial times p to the x power, that's lowercase p, times q to the n minus x power. Now, breaking that down real quickly, p, this lowercase p, represents the probability of success that we're dealing with in our problem. Q is the complement of that. It's the probability of failure. Now, we always know that P plus Q is always equal to 100%, or 1 if you're adding it in decimals. But that has to always happen. If it doesn't equal out to be 100%, that means that there's some other outcome that could occur, and that would mean that it's not binomial. So in order to be binomial, you must have a probability of success and a probability of failure that add up to be 100%. X, that is in the formula here, represents the number of successes that we want to have. So in this case, we want to have this number of successes. That will be the exponent to which we raise lowercase p to, and n minus x will be the power to which we raise q to, is the number of failures. So that must be understood going into the problem. We want to have a set number of trials. We want to have a number of successes that we want to have. And once we know those things, we can plug into this formula, knowing the probability of success and the probability of failure, and compute the probability that we will have that number of successes. Another thing about the binomial distribution of probabilities is that we can compute the mean, variance, and standard deviation of that distribution using these simple formulas. The mean of this distribution, any binomial probability distribution, will always be n times p. That's the number of trials that we have times the probability of success. The variance is always going to be n times p times q. Again, n is the number of trials, p is the probability of success, and q is the probability of failure. And of course, once we know how to find the variance, all we have to do to get the standard deviation is take the square root of that NPQ gives us the standard deviation. So again, finding the variance is the part that once we know how to do that, the standard deviation just kind of flows from that by taking the square root. All right, all of this said, let's go ahead and look at a few examples pertaining to these type of problems. This first example, the probability that Jennifer will score above an 85 on a math test is 80%. During the next 9 weeks, or the next quarter, there will be 4 tests in her math class. And what we want to know first off is, what is the probability that she will score above an 85 on exactly 3 of those 4 tests? So really what we need to ask ourselves is, do we have a fixed number of trials? In other words, do we know how many times we're doing something? And the answer is yes. We have 4 trials. So we do know what our n is in this case. That will be n. We're now asking ourselves, do we have a situation that's a success or failure? Let's see if I can write it out. Success or fail. Do we have a situation that's going to rely on a success or fail? And the answer is yes. We either make above an 85 or we don't. So that is going to be what determines whether we're successful or not in this problem. So based on that information, we know that n is 4, and we know that we have a p, probability of success, and we have a q. The probability of success is going to be based on this probability that she'll score. I guess I should underline the whole thing. Probability she'll score above an 85, and that probability is 80. So the end success in this problem is scoring above an 85. The probability that we'll do that is 80%, so that would be 0.8. And the probability then of failure would be not scoring above an 85. Well, if she does that 80% of the time, she's not going to score above 85 20% of the time, so that is the probability of failure. So knowing all of this, we're going to figure out exactly what number of successes we want to have, and then we'll go to the formula and use all this information. Well, we read real quickly that we want exactly 3 successes. Okay, that's our number of successes right there. So, knowing all of this, we know n is 4, we know x is 3, we know the probability of success, p, is 0.8, we know the probability of failure is 0.2, so we'll go to the formula, and that is going to be the probability of 3 successes is going to be equal to 4 factorial divided by 4 minus 3 factorial times 3 factorial times 0.8 raised to the power of the number of successes we want to have. Well, we want to have 3. So we will raise 0.8 to the 3rd power, and we will raise 0.2, the probability of failure, to the number of times we want to be failure. And that would be 1. If we wanted 3 successes, we'd have to have 1 failure. So this is our formula. Real quickly, simplifying this out is going to give us, let's see, 4 factorial over 4 minus 3 factorial, 3 factorial, all simplifies out to be 4. We're going to multiply that by 8 or 0.8 to the 3rd power, which is 5.12, or 0.512, excuse me, and then 0.2 to the 1st power is 0.2. So we multiply all that out, and we get a probability of 0.410. So basically, 41% is our probability that she will get an 85 or higher than an 85, excuse me, on 3 of those 4 tests. Okay, part B asks what is the probability that she will score above an 85 on fewer than 3 of those tests. Well, fewer than 3, we need to understand, includes several values. So what we have to do is figure out the probability, excuse me real quickly, the probability of all of the values that would be fewer than 3. That would be 2, the probability of 1, and even the probability of 0. If we can figure those out, that would be what we could add together to get the probability that she would get fewer or above an 85 on fewer than 3 of those tests. So we're going to figure out these and add them together. Well, you can imagine this might take some time, so we would use the table if we can, and that table is on page 770. If you're looking at this and you're using a different textbook, you would just use the binomial distribution table. That is on page 770 in our textbook here. So we will refer to that and make sure that we can use that table in this case. Well, in looking at this table, we have to first identify the n for our problem, the p, and all of the x's that we're going to use. Well, the n we already said was 4, p was 0.8, and x is going to be 2, 1, or 0. So we're going to work all those out or look all those up and find them. Well, if we turn back there, we identify n is 4. We find the location where n is 4 in the table. We move over to the column where p is 0.8, and then we look for the row in which x is equal to 2. Looking at that, we would find the probability of 2 to be 0.154. Then we would look for the probability of 1, and that's going to be right next to it as 0.026. And then we would look for the probability of 0, which would be 0.002. And again, all of this is in your book on page 770. Let me move that out of the way real quickly and talk about what we're going to do next. The next thing we're going to do is we're going to identify what the probability is that x is less than 3. And that's what we were actually asked to find. Fewer than 3, less than 3 is the same thing. Well, we get that by adding up all of these values, and we get 0.154 plus 0.026 plus 0.002 is 0.182. This is our answer for the question. And the question was, again, what is the probability that she'll get above an 85 on fewer than 3 of those tests? So we figured out the probability of 2, the probability of 1, and the probability of 0 scores above 85, and we added those up to get the probability that x would be anything less than 3. And again, the table is very useful when you have multiple issues that you have to get worked out and combine, like we did in this case. Let's look at another example. In this case, Joe bowls in a local bowling league. Over the past several seasons of bowling, he has gotten a strike, which means knocking down all the pins, 40% of the time. He will bowl 10 times in one game. That's a game of bowling. You roll 10 or bowl 10 times or 10 frames. Part A is asking us, what is the probability that Joe will get exactly 5 strikes in a game? Well, again, the question is this binomial? Do we have a set number of trials? Well, yes, we have 10 times we're going to bowl. So we know we're bowling at 10 times and one game. So that is the end. Do we have a success or failure? Well, a success in this case is getting a strike, and a failure is, of course, not getting a strike. So yes, we have a failure or success situation. So we're going to real quickly set this up by identifying what we're looking for. We know that n is the number of times we're going to try this or try to get a strike, and that is 10. We know that x, the number of times we want to be successful, is exactly 5. So we want to get 5 strikes, that's our x. We also know our p is the probability of success, and that is 0.4, 40%. And q, of course, is the opposite of that, the probability of not getting a strike. Well, if the probability of getting a strike is 40%, the probability of not getting that strike would be 60%. And then we're going to go to our formula. Real quickly, the probability that we get 5 strikes in a game based on the formula is equal to 10, which is n factorial, over 10 minus 5 factorial times 5 factorial. We're going to multiply that times the probability of success, which is 0.4. We're going to be successful 5 times, so 0.4 to the 5th, times the probability of failure, which is 0.6. We're also going to be fail 5 times. So this is our formula. And real quickly, I will kind of go through this by canceling some things out, and I'll let you kind of work this out on your own. As you do that, I'm going to go ahead now and jump in, since you probably paused it and did that. We can simplify this down to 30,240 divided by 120. That's after you cancel out 5, 4, 3, 2, 1 out of the numerator denominator. 0.4 to the fifth is, let's see, 0.01024. And 0.6 to the fifth is 0.07776. I guess I can go ahead and simplify this. That 30,240 over 120 actually simplifies out to be 252, which we're going to multiply all that. Now when we do all this, we get our probability to come out to be equal to, and I realize I just wrote that on the line, but it was still the same answer. It comes out to be 0.201. Okay? That's what we get from this. So the probability of rolling exactly 5 strikes in the game in this situation is, that again, making a mess there, 0.201. So that's roughly 20% chance that Joe is going to bowl exactly 5 strikes in the game. Now the next part of the question is, what is the probability that he'll get at least 7 strikes in the game? Well, at least 7, you need to stop and think for a moment about what at least 7 means. That means the probability of 7 or more, which would be 7, 8, 9, and 10. So we have to figure out the probability of each of those events, and hopefully you realize by this point we will just add those up. Well, again, we can go to the table here. We know all this information. We know that P is 0.4, Q is 0.6. We know that N is 10. So we're just going to go to the table and locate these values. So in doing so, I'll give you a quick second to do that. In doing so, you should be able to find the probability of 7 is 0.042. The probability of getting exactly 8 strikes in a game for Joe would be 0.011. The probability of getting exactly 9 strikes in the game would be 0.00, sorry, my smartboard is giving me a little issue this evening, 0.002. Now, if you look at this problem in the table and we look at the area where x is equal to 10, you'll see that there is just a blank space there. There is nothing. Some of you may have a nicer table that has some more values here, but in this case, in our textbook, we're seeing no value there. That just means that this is basically 0. Okay? It's not impossible, but it's so unlikely that the percentage is less than 0.000. So that's what we'll count it as. So again, we're going to add all these up, and we'll see that the probability that we get greater than or equal to 7, which is at least 7, is what we get when we add all these up, and it's not very likely. It's 0.055, which is about 5.5% that we get for that. So Joe, according to this problem, is going to get at least 7 strikes 5.5% of the time out of his games. Okay, let's continue by looking at this third example, or this last example, excuse me. Hospital records show that 85% of the patients that they treat for a certain fatal disease end up surviving. If we were to randomly select 8 of their patients that are being treated for the disease, in part A, what is the probability that all 8 of the patients will survive? Well, again, this is a binomial situation. As we've said, we have a specific number of trials, that's 8, the 8 patients that we're looking at. We have a success and a failure. In this case, success would be surviving the disease after your treatment at this hospital. So we're going to look at that. We have a set number of successes that we want to have, and that's all 8 of the people that we're working on or working with. So we'll go ahead and use that formula. That would be the probability of 8 is equal to, and again, I'll go over here real quickly, n is 8, x is 8, so don't get confused by that. P, the probability of success is 0.85, and the probability of failure in this case would be 0.15. So as we look at this and put it in the formula, that would be 8 factorial divided by 8 minus 8 factorial, 8 factorial, multiplied times 0.85 to the 8th power and 0.15 to the 0 power. That's not a very good zero, but as we work all this out, you will see that this comes out to be 1. So that's 1 times 0.85 to the 8th power and 0.15 to the 0 power. This part is also 1. So basically what we've got to find is 0.85 to the 8th power. That is or thereabout 0.272. So the probability, if we pick 8 patients, the probability of all 8 of those being survivors in this case would be 27.2%, or 0.272. Looking at part B, we're asked to find the probability of more than 6 of them surviving. Well, in this case, the probability that x is greater than 6 is actually going to be equal to what we get when we say the probability of 7 plus the probability of 8. And we may want to go to our table and look these values up. And one thing I want to mention here is that we can't use the table. There's no table for this case. Our version of the table, and you might find some versions that do have it, but our version does not have a p equaling 85%. It jumps from 80% to 90%. Most tables would do that because they only use the common values. So since we can't use the table, we're going to have to work this out by hand using the formula. So what we'll need to find is the probability of 7 and the probability of 8. And then we would have to add those two together to find out what the probability that x is greater than 6 is. So let me jump in and do that real quickly. Move that out of the way. Probability of 7 is going to be equal to n factorial, which is 8 factorial over 8 minus 7 factorial times 7 factorial, all times 0.85 raised to the power of the number of successes we want. And in this case, we want 7, so that would be 0.85 to the 7th power, and the leftovers, the probability of failing, to the 1st power, because we would fail 1 time in that case. So what we get when we do that, real quickly, 8 factorial over 8 minus 7 factorial simplifies to be 8. So we have 8 times 0.85 to the 7th and 0.15 to the 1st. That is going to be equal to, let's see, 0.385 when we multiply all that out. Now that's just the probability of 7. So the probability of 7 is 0.385. Lucky for us, we already did the probability of 8. If you look up here, it's right up here on top of the problem from part A. We found out that was 0.272. So I won't do that again. So the probability that x is equal to 6, or excuse me, x is greater than 6 is going to be equal to the probability of 7, which we said was 0.385, plus the probability of 8, which we said was 0.272. And that gives us the final probability of 0.657. So if we looked at 8 random patients at this hospital dealing with this disease, the probability that more than 6 of them would survive would be 65.7%. Now, one interesting thing is, if we looked at this, there's a couple more questions down here. Part C asks us, what is the expected number of patients to survive out of the 8? Well, we're going to take a random sample of 8 patients, and we're asked what the expected number out of those 8 patients would be to survive. What we're actually asking is, what is the mean number of patients? Remember, expected value or expected number is the mean. So what we're actually going to do is we're going to reference, if we go back to the beginning, you'll recall that mu, the mean, is equal to n times p. So all we have to do to find this is, for this problem, n was 8, p was 0.85. So we multiply those together and find that the mean is 6.8. So we would expect out of every group of 8 patients that we had, it would balance out to be 6.8 of the patients out of the 8 that we picked would survive this disease. Part D asks us, what is the standard deviation of this distribution? You'll remember, or hopefully remember, that the standard deviation formula for a binomial distribution is the square root of n, p, and q. So in this case, that would give us the standard deviation equaling the square root of 8 times 0.85, and q in this case is 0.15. So we multiply those 3 together, and we take the square root of that, and it's going to give us approximately 1.01 is what we would find for our standard deviation. So this distribution has a mean of 6.8 and a standard deviation of 1.01. Okay, well that's all we have for today to look at. The key to binomial probabilities, again, is learning to pick through the information. Learn to identify, first off, whether it is a binomial probability issue. Does it have success and failure? Does it have a set number of trials? And then you want to be able to identify what n is, the set number of trials. What is that? How many successes do we want to have? What is the probability of success? What is the probability of failure? And then plug everything into that formula and use that formula to get your answer. Of course, whenever we can, we want to be able to use that table. It saves us a lot of time. It helps us out quite a bit as we're approaching this. So take some time, practice on the problems that you've been given in class, and good luck.